Right, to finish this part of the unit, we want to just do a little bit of a theory chat. So if you've ever kind of walked along like the street or along a hallway, sometimes you may notice you have a little bit of a swagger. Sometimes you might notice that your arms seem to be kind of swinging side by side, almost like they're doing them on their own, without you having to actually like swing them yourself. They just kind of naturally do that. And sometimes you've also found like, if you're in a pool or like when you were a kid playing in a bathtub, you probably tried to make waves with your hands, but you found that like you could only make a wave if you move your hand kind of in the right way. Well, all of this has to deal with this concept of resonance or resonant frequency. And this resonant frequency or resonance frequency, it's a special property of an object, and each physical object will have its own resonance frequency. So when we have mechanical systems, sometimes, especially when we want to overcome friction, we may have to put a little push into the system to kind of keep it going. So a great example of that, those of you that have siblings, you've probably at some point, especially if you have younger siblings, you've probably had to push them on a swing at some point. Now, if you push them and they don't do anything, eventually they're going to come to a stop. What you're going to do, though, is you're going to push them, and you'll find that there is a sweet spot when to push them. Like if you push them at the right spot, you're going to be able to make sure that they continue moving with kind of little effort on your part. There's also some other times if you try and push them at a certain point, it's not actually going to work that well and you'll have exhausted a lot of effort. What you're doing is you are acting as a forced frequency or a driver. You're an external object providing a continuous push to something else that is moving in repetitive motion. You are causing it to continue to move. Now, what we find in physics is that forced frequency, so that frequency from an external object, if it happens to be close to or matches exactly the resonant frequency, so kind of the natural frequency of that object, you're going to find that really little force is going to be required to move the object. So this is again why, like, if you kind of apply your push on a child on a swing with a frequency that's very close to the actual frequency of the child moving on the swing, your efforts will be very minimal. You'll get the force required to get them moving, and you won't have to exert a lot of effort. And we're going to look a little bit more at that. So the resonant frequency of an object will not change. The driving frequency can. Like you can certainly supply a force at varying frequencies. You can change that, but the resonant frequency won't change. It depends strictly on the materials of the object. So it's kind of a physical property of that object. Now, when we have a forced frequency that's close or matches the resonant frequency, what can happen is we can start to create really large amplitudes of oscillations. So, we could kind of start going from something like this to something like this. Like we could start to build up the energy in this object. So doing this by matching those frequencies or getting them really close to one another, what we're going to do is we're going to kind of exhibit this characteristic known as mechanical resonance. So mechanical resonance can either be a really good thing. A lot of times, though, it's also not a good thing. It's actually very bad. So the big thing with engineering is resonance is something that you have to be really careful with. So for example, if you're going to build a really tall skyscraper, you have to be wary of resonance. So in a windy day, the wind is going to push up against your skyscraper, and it's going to push the building a little bit. Like if you're ever in a building, like a skyscraper, it is going to kind of rotate or oscillate about a point rather. Like the Burj Khalifa, the tallest building in the world, if you get to the top floor, it does sway about 10 meters on each side of its equilibrium point. So that is something that builders have to be wary of. The building itself is going to have its own resonant frequency or its own natural frequency. Now, something that could happen is, let's say there's a wind passing by and it happens to have a frequency that's really close to the natural frequency of the building. What's going to happen is it's going to be much easier for that wind to impart its energy onto the building, and then it could start to build up those oscillations. So the building could, in theory, rock back and forth more and more. Eventually, it could fall down. We don't want that. That is a danger. So what engineers would do now in modern skyscrapers, you're going to have this giant kind of ball that's going to take up several floors of the building, and this is referred to as a tuned mass damper. What it's going to do is it's going to try and cancel out the oscillations of the building as best as possible. So for example, in a windstorm, if it's kind of pushing this building to the left, computer signals from all these readings throughout the building, they're going to tell this tuned mass damper to swing a little bit to the right. What that's going to do is that's going to lessen the effects of the oscillation. What they are trying to do is they are trying to do this process called damping. They are trying to decrease the overall amplitude of the system. And bridges, this is also, and this is more famously known for a big screw up. Bridges, they want to make sure that they are streamlined. What this means is that they want the air to be able to pass through the bridge without imparting a lot of energy onto it. Because once again, if the frequency of that air passing through happens to be close to the natural frequency of the bridge, you could kind of start to cause the bridge to wobble. And then, if that energy keeps building up, it may eventually continue to get greater and greater in its wobbling, and you may have a disaster on your hands. And that did actually happen in 1940 at the Tacoma Narrows Bridge. So this was a real famous example of mechanical resonance causing complete destruction of a structure. So the Tacoma Narrows Bridge, here's kind of a picture of what's going on. So there was a very small, well, I shouldn't say small, but there's a wind of about just a little over 40 miles per hour, and it happened to be passing through the bridge. And what had happened is you can't really tell much from a still photo, but the deck of the bridge was starting to kind of twist and contort. And then as the wind picked up, that twisting and that contorting became much more vigorous, much more violent, and then eventually the bridge ended up collapsing because it couldn't handle all that stress. So luckily no one died. There was a dog that died, but no people actually died in this accident, and that was very, very lucky. But that really forced engineers to start considering this whole idea of mechanical resonance. By sort of not taking that into consideration, well, eventually they lost their structure. So they did end up rebuilding the Tacoma Narrows Bridge. It's in Washington State. The new one is still standing today. But whenever you're dealing with engineering of any kind, like with structures, mechanical resonance is something that you have to be really careful of, just because it can have seriously destructive powers.